All right, here we go. If you hadn't had a chance to watch the video, you gotta watch it. Here's some slides, pictures from it. Do, do. Reduction is not stereospecific, then how can our products be geometrically pure? Nice, right? So check it out. Today we'll do amines, and we'll skip chapter 22. We might come back for a couple of my favorite reactions in that chapter, but it depends on the time. I don't want to cram too much in at the end here. The chapter 23, Beta DiCarbonyls, is what we'll skip to. So yeah, here we go. We got finishing off week 15, which is really week 31 of the 2 semesters. All right, so nylon synthesis is online. I got, last I checked, 24 turned in. They all get 2 points extra credit, and regardless of their score. Well, that'd be silly. What if you turned in nothing? Would I give you 2 points? I don't know if I would. So turn it in, and I tell you what, you can still get the extra credit if you turn it in by midnight tonight. When I say that, I mean Wednesday, the 13th of May. Exam 3 average was great, 89%, high of 100%. Man, it took a long time to grade. Who wrote that thing? Oh, yeah. Yeah, that's right. Anyway, so it looks like you guys have learned so much. You're mechanism masters now. So do the exam corrections there in the Canvas area, assignments, exam corrections. Or the key is in under assignments. Exam corrections, exam 3 corrections. So check out the epic paper airplane video. I was telling you, if you haven't already, watch it again, enjoy it, have fun with it. I've watched it a bunch. Keep turning in lab reports, homeworks, and stuff. And I'd like to have the final exam on the same day, preferably the same time window, but I don't know if that's going to happen. A lot of students say they have to do it on Wednesday, and some even said they would prefer Thursday, so I guess I'll kind of do it like I did before. With the lab exam, I'll just default Monday, Wednesday. Students take it Wednesday unless they want to take it Thursday. Just let me know. You could take it Thursday. And then Tuesday, Thursday people would take it Thursday, but unless they want to take it early because they might have like, oh, I have math and physics on Thursday. They can take it early if they want. Just let me know. And let me know by emailing me, but don't do a reply to one of my big emails because I get all mixed up with my emails. Like if you reply all to an email that, not even reply all, if you just reply to me, to an email that I sent to the whole class, it sometimes is really hard for me to find it in my email auto organization stuff. It's crazy. But if you send me just an individual email just from you, it's easier for me to get. So do that, please, if you want to change your time. If you don't have to tell me anything. And then, here, let me actually pause this guy. Where is it? Oh, there's Kaylee. Oh, wait. Boom. Magic. All right, she didn't even have her wand. Okay, so back to here. We got the I got these times up. So pick a time. If you're in the Monday Wednesday lab and you want to take it this time, just don't do anything. Just take it that time. If you're in the Tuesday Thursday labs and you want to take them these times, your normal time, just tell me. If you want something different, tell me. Okay, I put new homeworks online. The 19's been up for a while, and then 20 and 21. I put it 20, homework 20 up, chapter 20 homework. Not too long. And then I put up chapter 20 and 23 because I skipped 22. So that one you've already had before the exam. These are normal 3-point homework assignments. I tell you what, since this is last minute, if you do that homework, it's 2 points extra credit. And I made up new discussion areas. So when you have questions about particular chapters, these new chapters, it's best if you ask them here. That's why when I answer here, everybody could benefit. But of course, if you have like a personal question about something that just applies to you, you don't have to answer it here. You can ask it here. You can email me. And locker checkout. So I'm gonna be doing locker checkout after the semester. I did look through the lockers a little bit. The one time I've been in since we've been off campus when I made the nylon. And I saw like, the normal stuff. I saw some banana oil in there or something. So we'll be cleaning all that stuff out. But then I saw like lab coats and goggles and things. So if you want those, we're going to like bundle them up and put your name on it because I know whose locker's who. But if you're like, it's cool, I'll donate it to the next year's class, like lab coats and goggles. Just let me know and I'll give you extra credit for it. I said 1 point? I'll give you 2 points extra credit, let's say, if you want to do that. Donate goggles or lab coats. And or lab coats. So if you want your stuff though, it'll be organized and taken care of, don't worry. We'll get it back to you eventually. Looks like Placer's opening up now. We're one of the few counties. We have such a low rate of COVID right now. It's great. We have only 8 patients, it says, in the hospital with laboratory confirmed COVID, and only 2 are in ICU. So we only have 2 ICU beds being used up for COVID right now in all of Placer County, where we have like 400,000 people about. So that's great news. The shelter in place has really worked, and maybe we're just lucky, I don't know. So we're starting to open up. So I don't know, my gut feeling is fall. We'll be on ground again, but we'll prepare as if we're not. So we'll see. All right, off to chapter 21 again. All right, back to chapter 21, amines, and now we're on outcome 6, amine synthesis. And for this one, there's a number of ways we're going to synthesize amines. But first I want to mention a potential problem with synthesizing amines. Let's say you wanted to make this particular amine, ethylamine. And you wanted to make it just from like an SN2 reaction. Let's say you thought, oh, I could make that from the bromide, and I'll just add ammonia, and I'll get my ethylamine, right? This is a primary amine here. Will I just get that primary amine? No. You'll also get, let's say you used like 2 equivalents of this, right? 2 equivalents. You get the ammonia and the bromide. So you can see the amine adding, kicking off the bromide, and then another ammonia deprotonating it, another amine deprotonating it. But the problem with it is you'll also get dialkylation, because the amine will add to the bromine again. It's still a good nucleophile, and you can get trialkylation, because that's still a pretty good nucleophile too. So with SN2, you can get over-alkylation. Now, sometimes you actually want to over-alkylate. You'll add just an excess of this, and you'll just fully alkylate it. But if you just want monoalkylation, there's a different ways to do that. We'll discuss A, B, C, D, E, 5 of them. I should know that off the top of my head. 5 different ways to monoalkylate. Oh, before I start to do that, I want to also, I remembered after I recorded the intro, I thought for the donation, if you want to donate your goggles or your lab coat and or for the 2 points extra credit, I'll give you 2 points whether it's the goggles or the lab coat or both. I made a folder on Canvas under extra credit, and it says donate goggles and or lab coat. And if you just write a little note on this paper and upload it there, say you're going to do that, I'll give you extra credit, and then I don't have to worry about returning those things to you. But don't feel pressure that you have to do that. Okay, so let's talk about this. The first way we have to do this is a way we've already learned. It's to use a nitrile, make a nitrile, and then reduce it with lithium aluminum hydride. So let's say, for instance, if I wanted to make this, if I want Actually, I'll switch it up. And I'll do that one first. I want the ethylamine. How can I make that? I can do a retro of it. You just take the amine and say, oh yeah, this can come from nitrile and reducing with lithium aluminum hydride, and the nitrile can come from bromomethane and say sodium cyanide. The 2-carbon monoalkylated amine, primary amine. So 1 carbon, 2 carbons. So here's my synthesis. Add sodium cyanide and a polar aprotic solvent to favor SN2. Let's go with something we haven't done as much. Let's do, oh, remember DMF? Dimethylformamide. This one is aprotic because it has 2 methyls, dimethyl. 2 methyls on the nitrogen, no hydrogens. So, okay, it's polar from the carbonyl in there. It's aprotic, so it's good for SN2. Gets out of the way of the nucleophile. All right, we got our nitrile, 2 carbons. Then we just do lithium aluminum hydride reduction. So that's lithium aluminum hydride in diethyl ether initially. And then we have to do an acidic workup to deal with the aluminum hydride stuff. And when we do that, it won't give us this amine initially, it'll give us the ammonium. So we'll have to do a 3rd step of sodium bicarbonate or some kind of base like that. Okay, and that will give us our monoalkylated amine. It won't add more than 1 ethyl because the cyanide just can only add once at that point. Okay, next step is another way to make an amine, make an alkylated amine without over-alkylation is to reduce a amide. Okay, so let's see, let's say I want this guy. I want that guy. What can I get it from an amide? Well, it could come from an amide like that. That's been reduced by lithium aluminum hydride. So let's try to do it from different ways. One way we can do this is you could have, say, the carboxylic acid, and you were to add ammonia to that, heat it up, you can make the amide. Then you reduce that lithium aluminum hydride, diethyl ether, acidic workup, which initially would give us the protonated amine, the ammonium. So then we'll follow it up with the sodium bicarbonate. And this will give us our desired monoalkylated amide. This could also, this amide didn't have to have the H's. So it could have been a dialkylated, so maybe you want dialkylated, but you don't want to be alkylated like 3 times tertiary, it's trialkylated. So, yeah. This amide could have come from other things too, right? You could have also used, so you have this that can work. You can also make it from the acid chloride. It does the same thing, or the anhydride would give you the same thing. So lots of ways to do that. Making the amide. Did I say amide? Yeah. And you make the amine at the end. I hope I'm not mixing up amide and amine, sorry. Amide, amine. Okay. Azide's pretty cool. This is a new way. So azide is a N3-. It's got a nice Lewis structure to it. You can draw it this way. You got a minus on this nitrogen, a plus there, a minus there. This is a good, like, general chem. Can you draw the Lewis structure and resonance for this? Because you can also see a minor resonance structure like this, where you say have the triple bond here and then a double minus on the end. Middle nitrogen always has a plus charge. It's kind of like the nitro of nitrogen. Okay, so, and then you could do it the other way too. So the azide is a very strong nucleophile, and it's because of that, it's actually it's a poison. In biochem, it's used often to, like, you make very dilute solutions and you store your equipment with azide solutions to keep microbes from existing in your equipment before you use it, and then you rinse it out good right before you use it. Azide, what are we going to use that for? Let's say I want this. Make it a longer one. Say I want this amine. How can I do it with an azide? This amine can come from the following. From the azide. Let me make sure I'm doing this right. 1, 2, 3, 4. 1, 2, 3, 4. This can. This is often written up as this as well. Just N3. One, 2, 3, 4, because it's overall neutral. All right, so what do we get that from? That can come from, oh, how do we do this? This is a reduction with lithium aluminum hydride. I'll do it in the forward direction. And that can come from a bromide and azide. You know, since we said it's a very strong nucleophile. It's interesting, it's a double-sided nucleophile. Either end of the nucleophile can react. So for the synthesis of this, you would just take your electrophile, your bromide, and react it with usually sodium azide. And polar aprotic solvent, maybe HMPA, hexamethyl phosphorus triamide. Remember that one is also polar, so you can see that polar phosphorus to nitrogen bond. Phosphorus loves oxygen, and then the nitrogens have to have methyls so that they're not protic, because having a hydrogen on the nitrogen would make it protic. It can pi bond. So this is 1, 2, 3, 4, 5, 6 methyls, hexamethyl phosphorus triamide. So HMPA, and you get your azide, and then that's just straight SN2. And then what you do next is lithium aluminum hydride reduction again. We use lithium aluminum hydride a lot for this stuff, huh? And it will make the amine under acidic conditions, so it'll be the ammonium, which you'll deprotonate with sodium bicarb. And you'll have your desired amine. I'm not going to go over this mechanism. Just know that that's how you use it, but I won't ask you to do the mechanism. You can probably see a little bit of it. Maybe the hydride adds. It's going to produce nitrogen gas. I bet if you tried to work out the mechanism, you'd get a pretty good idea. You'd probably get it or have a real good guess at it. So that's another way to make amines. So to make amines that you don't have to worry about over-alkylation. The three ways we talked about so far is to reduce a nitrile with lithium aluminum hydride, to reduce an amide with lithium aluminum hydride, and to reduce the azide with lithium aluminum hydride. So they're all pretty similar. And we'll do a couple more, two more that are not as similar, but they're really cool ones. Next up is the Gabriel synthesis. This one's a nice one. It involves phthalimide. So here's phthalimide. So phthalimide is related to phthalic acid. Have you heard of the phthalic acid? It's something that you used before. So that's phthalic acid. When you have two carboxylic acids on a benzene ring, and they're ortho, and you can make the phthalimide just by adding ammonia and heating it up. So this is the phthalimide. It's kind of interesting to say phthalimide. Yep. So if you take the reason why I'm saying you've used this before, if you deprotonate this, if you add just one equivalence of, say, sodium hydroxide, make it potassium hydroxide, then you'll make potassium hydrogen phthalate. Do you remember that? Is it ringing a bell yet? Anyone? Potassium, hydrogen, phthalate, KHP. That's right. Remember your titrations? And you did over and over. It's clear, it's just getting pink. Oh no, it went away. Oh, it's bright red. Start over. So yeah, these are from your KHP titrations. Use this acid to titrate a basic solution of sodium hydroxide usually, and then use that sodium hydroxide to titrate acid. So yeah, KHP, potassium hydrogen phthalate. So why are we using this phthalimide again? Well, actually we didn't use it, we used something like it again. So the reason why is if you deprotonate this, you could deprotonate it with just something like KOH will work. Because the pKa of this guy, I think it's 8.3, let me see. Yep, 8.3. So is this a product favored reaction? Yes. We went from pK 8.3 to pKa about 16 product paper. And now this will add an alkyl group. It can do SN2, it does it well. And when it adds the alkane, it only adds it once. Oh, but before I do that, why is this pKa so low, 8.3? It's because this has resonance, huh? You can resonate to that carbonyl and to the other one, so do-yo the resonance there. And it's a good nucleophile that we can now alkylate. So I didn't actually say I wanted to make a particular one, but I'll just make one. I'll go with secondary amine this time. It can do secondary. It's an SN2 reaction. So when I react these, I will get following. You can see that happening, right? Just straight SN2. Okay, I started this whole conversation saying we won't over-alkylate the amine. So why won't this lone pair just add another? It's because that lone pair is not nucleophilic. Why is that one not nucleophilic? Resonates to the two carbonyls. That ties up its resonance. Actually, we've been talking a lot about this. If I look at the nitrogen here and the carbonyl oxygen, which is more basic and nucleophilic? More basic, more nucleophilic, more basic, more nucleophilic. So that guy's not very nucleophilic at all. So it just adds once, just adds one alkyl chain. And that's the good thing about Gabriel synthesis, but we haven't really made an amine yet. We need to finish it off. All you do to finish it off is add a base. You can do it under basic or acidic conditions, actually. Generally, it's done under basic conditions. You can add, say, sodium hydroxide, aqueous, and then that's it. I don't know why I'm doing 1A. Boom. What you get out of this is the phthalate and the primary amine. No need to add another sodium bicarb step because this is under basic conditions. That guy will be doubly deprotonated, making it very water soluble. This can be extracted into an organic layer and you're good to go. I'm debating on whether I'll show you the mechanism for this because you already know it. It's just basic hydrolysis of an amide twice. Hydroxide adds, eliminate. I'll do it. A good review of the amide hydrolysis. So the mechanism, I guess we can, this part's so obvious, you can do those. But let's do the hydrolysis. So the hydroxide's a strong nucleophile. Those are weak electrophiles, but they work. The nitrogen actually, it donates into both of them through resonance and withdraws through induction. but the donation is split in half. So it's overall, each of these carbonyls is a little bit activated. They're a little more positive than just a regular amine. You get addition. Strong nucleophile adds right away. Tetrahedral intermediate. Then, do we have a good leaving group? Not really. But we have an okay leaving group here. And there's water around. So let's do the whole protonated on the way off. So I'm going to drop my lone pair down, and I'm going to have this swing out and be protonated on the way out. And I have my elimination right after my addition. So I've already gotten one of the hydrogens on here, of the two that are coming onto it. This carboxylic acid, it's in a basic solution. Will it remain that way? No. It's going to get deprotonated. I'll do that next. I think you guys are really good at mechanisms, so I'm hoping when I go through this kind of stuff, you're like, yep, that makes sense, that makes sense. There we go, and then another hydroxide strong nucleophile is going to add into the other carbonyl. Which carbonyl do you think was more reactive, this second one or the first one? The first one's more reactive. The first one, the resonance is being shared between the two carbonyls donation, so this guy's got a full resonance donation from the nitrogen, but the hydroxide is a strong base. So strong base, strong nucleophile. And I get, again, another tetrahedral intermediate. All right, and then I will do the elimination. Same as before, with the leaving group being protonated on the way off. So we have our amines, monoalkylated, not overalkylated, and then just finish it with adding the sodium hydroxide, deprotonate the last one there. So I'll say you have that last step. So hopefully this is all just like, oh yeah, I get it. He didn't have to do that mechanism. The last amination, the last amine synthesis we'll do is reductive amination. This one is my favorite. This is the one that I'll most likely have on the final exam to do this overall reaction and the mechanism and understand it. It's got a lot of good stuff in it. So this is how it works. You could take a ketone or an aldehyde. I'll take a aldehyde, say, this time. And you can add an amine to this and some reagents, new reagents. Oh, I said it'd be an aldehyde. And add some new reagents to make alkylation of an amine where you just alkylate once. So let's go with like a methylamine. So yeah, this amine already is alkylated once, but see, I want to alkylate just one more time. I don't want to over-alkylate it. I don't want to add 2 more alkyls to it, just 1 more. So I'm going to add this. The way I'm going to do it is I'm going to have that amine, and I'm going to have this new reagent, sodium cyanoborohydride. So we've seen sodium borohydride before, where it's sodium boron with 4 hydrogens. This one we have sodium boron with 3 hydrogens and a cyanide replacing one of the hydrogens. Sodium borohydride. And then usually a solvent like ethanol, similar to sodium borohydride reductions, right? And an acid like tosic acid. Usually you'll have it at a pH of about 2. If you just put tosic acid for our purposes, you're fine. Okay, what happens in this case is you wind up adding that chain to the nitrogen. These 3 carbons right here, 1, 2, 3, end up adding to the nitrogen. Works out really well. And it's interesting that you can have all this stuff in together and it gets you right where you want. It reminds me a little bit of like a Robinson annulation where one pot synthesis where you have a lot of things going on and it all just works out. So let's give you a little bit of background before I go over the mechanism. This is a mechanism you're going to most likely see on the final. So first off, let's look at the reduction part. Okay, so remember when we would have, if I just took this aldehyde and I added sodium borohydride and ethanol, it will reduce the aldehyde to the alcohol, right? We know this. But if I take sodium cyanoborohydride, what we're using here, just with ethanol, no reaction. So what does that tell you? What's the stronger reducing agent? Sodium borohydride or sodium cyanoborohydride? Sodium borohydride stronger, huh? So sodium borohydride it's a stronger reducing agent, stronger nucleophile. So it wants to reach out. It wants to donate a hydride to the carbonyl of the aldehyde because I don't want a negative charge. It's whiny, right? So then you can say, hey, boron, look at you. You lost the hydride. No more negative charge. I want an octet. And then it just goes on and on, right? Oh, that's not going to be wiggled. Right? So sodium borohydride will do that. But sodium cyanoborohydride doesn't do it. So why does that not react? It's got 3 hydrides on here and a negative charge on the boron. Shouldn't the boron be like, I don't want a negative charge? So why is it a weaker nucleophile? Why do you think that is? Well, let's look at the cyanide and compare it to a hydrogen. Does this sound familiar? Comparing things to hydrogen. So the cyanide, it has an sp hybridized carbon. And how does that work in terms of induction? Is it more electronegative than hydrogen or less? Well, let's look back at our little trend here. So for electronegativity, we said sp3 carbons were pretty low in electronegativity. We'll even say they're less electronegative than hydrogen. And then what was next? Oh, the sp2 carbon, because it had more S character. S orbitals are closer to the nucleus, more electronegative. And even more electronegative is the sp hybridized carbon. It has 50% S character. So its electrons can get closer to the nucleus. And it's more electronegative than a hydrogen. So in terms of induction, that sp hybridized carbon is electron withdrawing. In terms of resonance, can it resonate into or out of the boron? No, boron's got 4 bonds to it, no p orbitals available to it, so none. So what is this guy overall? It's an electron withdrawing group. How's that going to affect the nucleophile? It's going to make the nucleophile weaker. So that's good. So we can have sodium cyanoborohydride in the presence of the aldehyde and not worry about getting the alcohol. Because we don't want this to be reduced. We want the amine to add first and then we want reduction. So let's carry on with our background. Okay, let me review the first thing we went over in the background for this mechanism. Sodium borohydride is a stronger nucleophile, stronger reducing agent. So sodium cyanoborohydride is actually a weaker nucleophile, weaker reducing agent. Makes sense, the cyanide's electron withdrawing, pulling away negative charge from the nucleophile, making it a weaker nucleophile. So we don't have to worry about the aldehydes or ketone, if we had it, being reduced by the sodium cyanoborohydride. Because if it was, we wouldn't get amines, we'd just get alcohols. All right, the next thing we have to talk about is how the sodium cyanoborohydride exists in an acidic solution. So it turns out that we already know sodium borohydride doesn't react with alcohols, because those are our solvents we use. But if I added an acid to this, like toxic acid, like we have here, we have toxic acid in ethanol, that can create that. This can react to make your, this would be with tosylate. What's going on there? Just straight acid-base chemistry. So I should have just showed you the mechanism first probably, but that's all right. So here we go. We got the borohydride. It's whiny, doesn't want that negative charge. I don't want a negative charge. And the protonated ethanol is a pretty strong acid. So it can react with the borohydride as a base. So if instead of trying to use sodium cyanoborohydride, we used sodium borohydride, it wouldn't be good right when we'd add the toxic acid. It would start to react. But the sodium borohydride doesn't react with just the ethanol. It's not as acidic. This is much more acidic, right? Okay, so sodium borohydride wouldn't exist well in an acidic solution. What about the sodium cyanoborohydride? That boron also has a negative charge. I don't want a negative charge. Will it react with the protonated alcohol in this acidic solution? Will it go over and deprotonate it? No reaction. So why is that? It's the same reason we saw here. The cyanide is electron withdrawing overall, right? Because the sp hybridized carbon is more electronegative than compared to hydrogen. And that makes it less base, makes the base weaker. Makes it less basic. I don't know what's with my blue pen. This is a brand new blue pen. It's like they have to warm up or something. Yeah. So that should be easy for you. The cyanide makes it less nucleophilic and it makes it less basic, which is perfect for our situation because we want this to exist in an acidic medium. And we're going to see as I'm going through all this, everything in this mixture is like a perfect storm. It all works out great to give you a good yield of that amine there. Okay, reviewing the background again. Sodium borohydride versus sodium cyanoborohydride. Cyanide's electron withdrawing overall makes the sodium cyanoborohydride a weaker nucleophile, weaker reducing agent, so it won't reduce the aldehyde to the alcohol, which we don't want. And it's a weaker base as well, so it can exist in this acidic medium. All right, while we're doing this reaction, we'll have a number of electrophiles around for this sodium cyanoborohydride to react with, potentially. So here are some electrophiles that are around. So the aldehyde itself is an electrophile. Does the sodium cyanoborohydride react with that? No, it's not strong enough because that's a weak electrophile, right? Okay, but this gets protonated. It's an acidic solution, right? Not a lot of it, but a little bit. And when it's protonated, is it a weak electrophile still? No, now it's a strong electrophile. Can it react with sodium borohydride? No. Yes, sodium borohydride for sure. Can it react with sodium cyanoborohydride? Yes. So this aldehyde, the aldehyde will not react with sodium cyanoborhydrate. It's hard to write that out and say it because you say sodium cyanoborhydrate. You say cyanide part before you put that out there. All right, it will not react with that. Will react with sodium cyanoborohydride. So that will react with it. So that could be a problem if this guy reduces the carbonyl here, I'll get an alcohol. How's that going to be taken care of? Because I said it's a perfect storm. But the good thing about this is, the amine is a better nucleophile and beats it out. Outreacts it. So instead of the sodium cyanoborohydride getting in here and reducing it, I'll have my amine. It gets in there first. So I'm gonna go over the whole mechanism. This is all just still background. The amine's gonna get in there, and you're gonna see we're gonna get what's gonna form if I have primary amine under acidic conditions with a ketone. I'm going to make an imine, right? Remember amines? We are going to get our imine because the amine's going to attack this before the sodium cyanoborohydride can. So I have my imine. So, will this imine be reduced by the sodium cyanoborohydride? Can a hydride come in and reduce this? What do you think? Do you think it will? What do you think? Let's compare an imine versus the aldehyde. Who do you think is a stronger electrophile? What's more electronegative, oxygen or nitrogen? Oxygen's more electronegative, so it should put more positive charge on the carbonyl than the imine. So which one is more reactive? The aldehyde. Does sodium cyanoborohydride react with the aldehyde? Nope, it's not strong enough. We established that in the very beginning. So will it react with this? Nope, that's even less reactive. So sodium cyanoborohydride will not, put here sodium oh my god, I'm getting so sloppy here, sorry. Sodium cyanoborohydride will not react with either. Either? You say neither or neither? Can you say either or either? Either? Yeah, I think you can. It will not react with either of those. No, it will not. But we have to get our reduced amine. How is this going to happen? What will happen? It'll be a bloody good show if you have the imine protonated. Now, is it a better electrophile? Yes, it is. That's what I'm on about. We've got a much stronger electrophile now. And this will react with the sodium cyanoborohydride. Oof. It's all right, I'm at the bottom of the board and I can't write, but keep calm and carry on with the sodium cyanoborohydride. There we go. Whew. Okay, so we've done our background. We are fully prepared to draw up this mechanism now. All right then, we're back. And we see here that's the, let's say the, oh, almost crushed myself. We see here we've got the sodium borohydride is much stronger nucleophile and reducing agent than the sodium cyanoborohydride. The sodium cyanoborohydride is only capable of reducing the protonated amine. It has to wait to that last moment. And it's a weaker base, so it'll exist in the acid. So let's do the mechanism. We'll have the help of Naruto, Nick's skateboard here with the old fat wheels. Let's do this. Alright, so we're under acidic conditions. The amine will be protonated by the tosic acid. This is nothing new. You've You've seen this over and over. We'll use the amine as our, oh, you know, yeah, we can use the amine. Yeah, let's do it. The amine can be protonated like that. Could be the ethanol as well, depending on, the amine is a stronger base, but there's concentration factors to consider. This is fine. Now we're going to take our aldehyde, which is a weak electrophile. We're going to protonate that, make it stronger. Right there you have it. Bob's your uncle. We've got a nice strong electrophile. Will the sodium cyanoborohydride reduce it? It could, but it's going to get outcompeted by the stronger nucleophile, the amine, on its way to be an imine, like we've seen before. There we go, we've got our nitrogen on the carbon. It's going to eventually be an amine. It's got its bond to that carbon now, and it's a good leaving group. It can come right off, but we want it to stay there. Don't go anywhere, nitrogen. Keep calm, carry on. Let's have you, maybe I'll use the ethanol this time. If it's the solvent, it might as well. You can deprotonate that. Be a proton shuttle. There we go. Now that nitrogen seems it's going to stay for tea. Here we go. And we've got to get rid of that pesky alcohol. It's not a good leaving group at this point. It's not ready to go. But let's call it an Uber. There we go. We'll deprotonate here. On your way. Tally ho. There we go, good leaving group. We can push that bloke right off. And we will, with a little push-pull. Nothing new at this point. Oh, let's add our arrows, there you go. Your lift is here. Oh. A bit sloppy there, getting excited. Nearly done. Water's off, and now we could carry on and deprotonate to make the imine, and it could go back and forth, but then we have our borohydride come along. It's not your normal sodium borohydride. This is a weaker version. And it would come on like so. There we go. We finally got our reduction. Reductive amination. Spot on. And you think we're all done, we should just stop there. We've got our two hydrogens onto our carbon 1 where the aldehyde was, and our boron should be happy. Are you a happy chap? I'm not happy with my negative charge. Are you happy now? Blimey, I've got no octet. Still not happy. And what happens with the amine? It will be protonated. I don't know why I'm kind of going Scottish now. I don't know if I was before. I don't know. I don't know what I'm losing it. I'm losing it, guys. So we protonate that. And we've got now our ammonium. Just gonna have to wait around a bit. Oh, I didn't even draw the second step there, did I? Oh, blimey. Oh, I have to add in an error note. This should be a 1A and a B of a base to come along and deprotonate the ammonium Let's see if I could squeeze it on this little tiny board here. There we go. Look at that little crumpet. Come along and deprotonate the ammonium. We've seen this many times. And then that bicarbonate will become carbonic acid just for a wee bit before it decomposes to CO2 and water. And we will also get our amine we so desire, monoalkylated. It already had one alkyl chain, but it only added one more. It was a monoalkylation. And there you have it, reductive amination. All right, so I made up some practice problems for you. So pause the video, try filling in the boxes, see how you can do, see if you can get them all right. Come back and I'll do it for you. And then for a bonus, for all the mechanisms we learned, we didn't learn every mechanism. We didn't learn the Azide lithium aluminum hydride reduction, but I bet you can do it. If you really want to get good, try to do all the mechanisms too. Okay, welcome back. So here we go. This first one should be really easy, right? We got the 3 carbons, and we are adding bromide. It's going to go to the secondary carbon because in that radical mechanism, the secondary carbon radical is much more stable, so that one will be faster to form because the transition state is endothermic, and the transition state looks like the secondary carbon radical, lower energy than the primary. Okay, now when I add the I get the bromide initially, my bad. And then the bromide becomes the cyanide, huh? There we go. So I added another carbon there. I'll call it A. So when I do my reduction, lithium aluminum hydride reduction, it makes the amine there. That's protonated and then deprotonated. So here's my final product. I've added a carbon and I made an amine. So with the nitrile, I add a carbon while I'm making the amine. That carbon A. What about with the azide, the sodium azide? Well, with that one, it does not add a, I'll write it out. This one does not add a carbon. And then when I want to make the amine here, when I reduce it, it will just have those 3 original carbons. Should be that red, but that's okay. So what do I do to get that? I just do the same as I did over there. Lithium, aluminum hydride, diether, hydronium, aqueous, that protonates it too, so you got that sodium bicarbonate. There we go. Pretty cool, huh? You can do it by adding a carbon or not adding a carbon. Okay, back over here now. So we know we have a very strong electrophile, acid chloride, and amines, medium nucleophile. So this is going to make an amide. It'll be your classic addition, elimination. Make sure you don't get confused and like have too many or too little carbons. So I have 1, 2, 3 there, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4. That looks good. And then when I do the lithium aluminum hydride reduction with amides, it just erases that carbonyl. So on this one, I added just 1 alkyl chain because I already had an alkyl chain to begin with. So I have a secondary amine, and it's 3 carbons on that side and 4 on that side. All right, next up, the Gabriel synthesis. So this one, the KOH deprotonates that. It'll do an SN2. The other lone pair, the second lone pair, it's not nucleophilic, so you only get mono addition, which we only want in this case. And I'm adding how many carbons? 1, 2, 3, 4. 1, 2, 3, 4. Looking good. Okay, and then when I add the sodium hydroxide, it's going to hydrolyze both sides, and I'm going to get your the phthalate and my amine that I want. 1, 2, 3, 4. So I start off here with the primary amine. And let's see what I get when I add this ketone. So this is different than our example one I used, that was an aldehyde. This one's ketone. And let's talk through this a little bit. The amine acidic condition is going to make the imine, and when it's protonated, this weaker sodium cyanoborohydride reducing agent could reduce at that point, blah, blah, blah. So you'll wind up with this. So I've got my 1, 2, 3, 4 carbon chain that was put on via the Gabriel synthesis. And then I've got another 4 that are put on during the reductive amination. So, and I wind up at the end with a secondary amine. Pretty nice, right? Do you get it now? Do you like it? Do you know what I mean? Alright, so we're done with chapter 21, amines. But we can't just leave on that note. We have to do a retro. Okay, I wrote up a nice retro for us to end the semester. Not yet. End the chapter off. Whew, almost the end of the semester. This one, I've got a 3 carbon chain, and it looks like 3, 3. And I got a cyanide, that's probably there, huh? And this one will have lots of ways to do it, actually, because we know now lots of ways to make amines. I'll show you some of them, but why don't you give it a shot first, pause the video, and then come back. Okay, welcome back. Let's do it. So our retro will be from this amine. I can try working on this side right away. I can say maybe, oh, this came from reductive amination. That would work, right? Is there another way to do that? I think that's about it on that side. I could have also disconnected here. Oh, yeah, I think I have to do something like that, that's right. This could come apart via reductive amination as well. We would just have to have an aldehyde over here. That would work as well. Or it could have come from reduction of an amide like that. So lots of options. I would practice them all. I'll pick, maybe I'll just pick This first one? Sure, I'll pick that first one. Oh, not the first one. I'll pick this blue one here. So, there's a lot of ways to make this one as well, but I'll try to make it varied. So what I'll do is I'll say this one comes from the ammonia, and I'm sorry, I could say from the ammonia, but I'm not. I'm going to take it back to the Gabriel Synthesis here. I was going to say this phthalimide this guy I can make as well from the ammonia, but yeah, I kind of have to, huh? Yeah, let's do it right. This comes from the phthalic acid. Which you've made during your titrations. You've protonated potassium hydrogen phthalate, KHP, to make that. And ammonia. Okay, and then this one can come from the alcohol, correct? And the alcohol can come from carboxylic acid, which can come from a cyanide, hydrolyzing the cyanide, which can come from the bromide and the sodium cyanide, and finally that can come from just the alkane. I paused because I was planning on having this attached at the end there, which you could figure out as well, but whatever. Alright, so let's try that retro. There's lots of other retros for you to doyo up here too. I mean, let's try the synthesis of that retro. Lots of other options to practice there. So the synthesis will be, let's start with this guy, and we'll go 1A, Br2, and light. B will be the sodium cyanide and DMSO. We've got our cyanide on here. And if we treat that with water and acid, say sulfuric acid, heat that up, that will make your carboxylic acid. But I need an aldehyde. There are ways, but we haven't learned them and we won't, to reduce a carboxylic acid partially, just reduce it to the aldehyde. But since we haven't learned that, we'll just do the full reduction. Lithium aluminum hydride, diethyl ether, acidic workup, aqueous. This will give us our alcohol, lithium aluminum hydride, and we just set all the way down the alcohol. And then I need an aldehyde, so I'm gonna, I took it 2 steps down in reduction, I'll bring it 1 step up in oxidation since we do know how to do that, the PCC. There was many of you on the exam who were doing, you wanted to take the aldehyde and make it into the carboxylic acid. So you would reduce it to the alcohol and then oxidize it. You don't have to. If you just took this and you went Jones oxidation right here, that will oxidize it to the acid because the primary alcohol goes to the aldehyde, then to the acid. So just a side note. Okay, so we have our aldehyde. We'll pause there. Okay, and then I'm going to work on that amine. I'm doing Gabriel synthesis style, yep. So I'll take the phthalic acid, And actually, these two, this is called phthalic acid when the acids are ortho to each other. If these two acids are para to each other, it's called terephthalic acid. Terephthalic. So you might have heard of that because if you polymerize terephthalic acid with ethylene, you get polyethylene terephthalate. Terephthalate. That's the plastic like water bottles and things. So it's a real common. And it could be also polymerized with another monomer to make the butyl hydroxy, you know, the BPA, you know, bisphenol A plastic, which is fine. Like I think our goggles are made of that. But if it's in a drinking container, you might get BPA in your system, which has estrogenic effects. And so a lot of bottle manufacturers brag about, oh, we're BPA-free plastic, which is kind of interesting because they don't tell you what they're replacing the BPA with. And the studies of the BPA, they've had large numbers of scientists study it. Some are like, it might be dangerous. Some are like, yeah, it's probably not dangerous. So it's interesting. Here we go. We got the phthalic acid. Oh, if we add the amine, heat that up, you'll get your phthalimide. Okay, so now we need to do we have we need what do I got? I'm getting confused. Okay, I got that one. I need the bromide, huh? Did I show that in the retro? I didn't. This needs to come from plus the bromide, huh? Which is that one, yeah. So that's fine. Okay, so this guy can be deprotonated, say with like potassium hydroxide first, and then I followed up with my bromide, which I haven't showed the synthesis of yet, but I will. I'll do it right here. Little sidebar. Okay, we're able to use bromide now. So this will give us our monoalkylated nitrogen. So why doesn't this nitrogen alkylate again? Because that lone pair is tied up in resonance. And we can get it off of the phthalate system by adding a base. Heat that up and we'll get our phthalate over here. Like that, and our amine, and we have almost finished it off. Yes, we just need to add it to the aldehyde. So we're going to add the aldehyde. Ooh, 1A, I'm not going to forget this time. Aldehyde, sodium, not borohydride, but sodium cyanoborohydride, ethanol, tosic acid. Sorry, it's always at the end of the synthesis end of the board I get sloppy here. Sodium bicarbonate. And there we have it, reductive amination. And that's it. Done. It's a good one, right? We're down with chapter 21. Chapter 22, we'll skip it for now. We might come back and get a couple things from it. My favorite things, maybe the benzyne, maybe the nucleophilic aromatic substitution. We'll see. But for now, we're going to skip ahead to chapter 23. This is a chapter about beta DiCarbonyls molecules. I think you're gonna like this one. It's kind of new, but not really. I'll convince you that it's not that new. It's using a lot of the principles we already know about. So here we're gonna start with some acid-base stuff. So what is the pKa of acetone? And compare it to an aldehyde and then to an ester. Okay, so for these guys, the first thing you want to look at is, first thing you want to determine is, when I say pKa, which hydrogen is the most acidic on the molecule? That's the one that it's implied that you want the pKa of. You don't want to know the acidity of the second or third most acidic, you want the most acidic. So what's most acidic? This end hydrogen here, right? There's only one type of hydrogen on acetone. So what's the pKa of that? How does that work? The pKa is 20. You probably remember me saying that from before. It's much more acidic than you might think because the conjugate base of it has resonance to stabilize it. Normally when we're deprotonating these, I'm using a stronger base, and that's okay. But the pKa value here is based on water as a solvent. So that's what I'm making, right? So this pKa is not 50 like an alkane because once you make the alkane anion, it's not just an alkane anion, I'm sorry, it's an enolate. It has resonance. So that negative charge is spread over both atoms. Okay, so we see why that's 20. The aldehyde is 19. It's a little more acidic. Why is that? It's because the sp3 carbon on the, I'll look at the other side. The sp3 carbon over here is a weak electron donor relative to hydrogen. So if it's a weak electron donor, that means it's going to make the acid a little weaker because acids want withdrawers to make them stronger. Okay, what is the most acidic hydrogen on the ester? It's these ones over here, right? Because if I deprotonate that, it'll have resonance like an enolate. And the difference between this ester and these guys is this group right here. And how does that affect the pKa? Well, let's review it a little bit. That oxygen by induction is electron withdrawing because it's more electronegative than hydrogen. By resonance, it's electron donating. It can donate into there, right? Overall, it's 2p plus 2p donation, so that's actually strong resonance there. 2p from the carbon, 2p from the oxygen. The 2p orbitals are overlapping. So the resonance wins out. It's overall an electron donating group. And not only that, it's a strong electron donor. So I said the sp3 carbon was a weak electron donor. It does that because of hyperconjugation. Remember, we say hyperconjugation, don't worry about that. What we like to think of it as it's less electronegative than hydrogen. Okay, so what does it turn out when you do the experiment for this? What's the pKa of the phenol? 25. Does that make sense in terms of our predictions? Hydrogen's a reference. sp3 is weakly donating. That makes it a little weaker acid. The ethoxy, strongly donating, makes it a significantly weaker acid. Pretty cool, huh? Okay, now we're going to look finally at beta dicarbonyls. Let's look first at a beta diketone. So this is a beta diketone. What do I mean by that? Where do I get this beta stuff? Well, since they're both ketones, we're gonna just describe one of them first. Let's say this is our reference on the left. This is my reference. That carbonyl carbon is a carbonyl carbon. What is this here? That's an alpha carbon. What's there? That's a beta carbon. So you can see it's got a ketone beta to the original ketone. So beta diketone. Okay, so now let's look at the acidity of this guy. Turns out the pKa of this beta diketone is more acidic than these other guys by a lot. pKa of this guy is 9. Went down a lot, huh? pKa of this one ketone is 20. Oh wait, yeah, 9, that's right. Okay, so what is it? Yeah, I think it's 9. 9, 10. Okay, so let's try to describe what's going on here. So where is it most acidic? Is it most acidic on the end carbons? Or is it the middle alpha to the both that's more acidic? What do you think? It's the middle one. Let's deprotonate it and see why. So if we take our dicarbonyl, we deprotonate the middle, di-alpha carbonyl, you'll see that you get a conjugate base with extra resonance. Because the anion here is got 2 carbonyls it can resonate to. So this lone pair can resonate to the right. And I randomly chose it to resonate to the right. It can also resonate to the left. I'll put a hinge here to see. Swings over like upside down windshield wiper thing. Swings up there. Pretty nice, right? So it's got 3 resonance structure, where just a single ketone has only 2 resonance structures. And so if you want, you can take further, you could draw a resonance hybrid for it. Oh, I didn't do a good job. Hybrid. Okay. So that negative charge is spread over a lot of areas here, huh? So there's going to be a lot of negative charge on the oxygens and less negative charge on the carbon, because carbon is less electronegative. But that negative charge spread over 3 atoms. Okay, so we see that the dicarbonyls, when they're beta to each other, they can be more acidic. Let's look at some other examples like this. What if I replace one of those ketones with an ester? Let's say I draw up this guy. So this guy is actually called a beta keto ester. So why do you think that is? Why beta keto ester? Well, remember, what was a higher priority, an ester or a ketone in terms of nomenclature? If you remember, there was a lot of the carbonyls were the highest priorities. They were all the higher priorities. Carboxylic acid was the highest that we have on our list. And ester beat out ketone. So the ester beats out the ketone. And relative to the ester, This is the esters carbonyl carbon, alpha, beta. So that's a beta ketoester. Okay. Next, if I want to talk about the pKa of this guy, I got to figure out where is it most acidic. Is it most acidic on the methyl here? No. Here? Nope. Here in the middle? Yes, because that's going to have resonance to both carbonyls. And it turns out that this is not going to have the same pKa as the diketone. It's going to have a higher or a lower. What do you think? We're switching out the methyl, which is a weak electron donor overall, for a ethoxy, which is a strong electron donor overall. So if you're strongly donating electrons in there, are you going to make that acid stronger or weaker? Well, going loud, try it out, and the pKa goes up to 11. So it made it a weaker acid, as you should have guessed, because more electrons means the glue that's holding this hydrogen there is stronger. Also, the conjugate base won't be as stable. More electrons adding into its negative charge. Okay, what about then finally a situation like this, where we have an ester on both sides? So where is it most acidic again? Here. And it's got two strong electron donating groups to it. So what's its pKa going to do? Is it going to go up, stay the same, go down? pKa is 13. It went up again, of course, because it's two strongly electron donating groups. It would be good for you to, just for practice, to deprotonate them all and draw their 3 resonance structures for each. Now for the Claisen condensation, which these pKa's will come into play. The Claisen condensation is a reaction where you take 2 esters and you condense them together. So if you look at this closely, you'll see we've got 1, 2, 3 carbons there, and then they show up 1, 2, 3 like that, and 1, 2, 3 like that. So let's look at the mechanism for this. The mechanism is an addition elimination mechanism, which we've seen a lot. And remember, with addition elimination mechanisms, you get addition, tetrahedral intermediate, elimination. And a lot of times you need to do some proton transfers in between. And that's the case with this one. So let's look at this guy. What can happen first? We need an electrophile and a nucleophile. You'll notice I drew this methyl pointing down. That's going to help you see it. So I need an electrophile and a nucleophile. Do I have a nucleophile? I guess the ethoxide. And the ethoxide actually will add into the carbonyl, make a tetrahedral intermediate. But then when it drops back down, it just makes the same thing. So that's constantly going on. If you want to match your base and your solvent with your ester's ethoxy group. Okay, otherwise you'll get transesterification. Remember that word? Okay, so what we need to do is we have this guy, which is a weak electrophile. We need to make it into we need some of it to be weak electrophile, and we need to make it into a nucleophile. So how are we going to do that? We can make the enolate of it. What's the pKa of the ester? It's about 25 because of the electron donating ethoxy group there. So we're going to deprotonate this, make a strong nucleophile. Is this reaction very favorable, product favored, do you think? It's not. Because you're making the ethanol, which has a pKa of about 16, and it came from the acid of 25. but it's okay. What we're going to do is we're going to have a step in this synthesis, this mechanism, I'm sorry, that's going to pull it all forward. So right now, it's not looking too favorable, but we do have some strong nucleophile that can now react with our weak electrophile. This is the ester we know is a weak electrophile. That's all right. Strong can react with weak. Hinging right there, I'm going to add into that carbonyl. Let me number my carbons, make sure I don't get confused. I've got 1, 2, 3. I'm going to leave off the ethoxy part. I got 1, 2, 3 carbons there, and it's adding to carbon 1, and then I got 2 and 3 out here. So let's put that together. When it adds, it's going to be, oh, this is, by the way, your addition step. We're adding to that carbonyl, and we're getting a tetrahedral intermediate. Draw it down here. Like so. So we had to do some acid base. We got our addition, and we got our tetrahedral intermediate. Right here. All right, so now after we have our tetrahedral intermediate, we start thinking, can we eliminate something? So what would be a good leaving group? The ethyl? No. This guy? It would be decent. That brings us back that way. What about the ethoxy? I do need to get rid of an ethoxy, huh? So yeah, we're going to use that. We're going to make that a leave. Even though it's not the best leaving group, we're going to have it come off under these basic conditions by having it be protonated as it comes off. So we got our elimination. I didn't number my carbons, but I need to, don't I? Why is there water? There's no water. This is ethanol. Sorry about that. Okay. So, I'm going to number things too to make sure we're right here. I got 1, 2, 3, and I had a 1, 2, 3 there. 1, 2, 3. 1, 2, 3. 1, 2, 3. There we go. Looking good, right? And you'd think we're done. We made it, right? What was the point of the acid workup? Maybe just to quench that? No, we're not done. Actually, the next 2 steps I require you to draw because they're the driving force of this reaction. They're going to make us get a good yield. We saw the first step wasn't very favorable. I'm not sure about this one. This one might be pretty favorable, but I don't know about this one being very favorable. This next reaction is very favorable though. What is the pKa of that guy? It's a beta keto ester. So its pKa was 9 for the diketone, 11 for the beta keto ester. So will this be deprotonated? Yes, and this reaction's product favored. I'll just go to one of the enolates. This product is not only going to happen, but it's this one's product favored, which can help drive the reaction to completion. So it's important to show that step. Azide Reduction. Okay, and oh yeah, let me just make sure. So it's pK of 11 there, pK of 16 here, so you can see that's going to help things out. And then we just finish it off with an acidic workup to give us our final beta keto ester. This reaction, it's not really new, huh? It's an addition elimination, and once you practice it a couple times, you'll get it down easy. It helps to draw your ethoxy or methoxy or whatever oxy to the left, and then have this on the right, I think, and practice this a couple times, because we're going to build on this in next lecture, but that's enough for today. All right, thanks guys.